How's it going? Basically, today I'm here just to give you um overview of the work um I was doing last semester, and my plan is to give an extended um final presentation just like last semester as I did, but it's going to be more related to the code base. Um, it's going to be more an analysis oriented and more detailed in terms of the data and the code actually implemented last semester. Um, so the data set we're working on last semester is called like a panel data set. We are primarily focusing on the public housing inspection score in the United States. So just to give you a bit of background, panel data obviously is basically a data set that is keeping track of individuals over a period of time, and there is some specific features for panel data. Each individual is called a unit, and it has double dimension. We can compare different time periods, but we can also, in another dimension, we can compare different entities. In this case, we can compare different states in the United States and or different regions in the United States. So public housing is basically the goal is to provide decent and safe rental housing for low income families, the elderly people, and presumably persons with disabilities. Um, the inspection score, I think this Wednesday, I didn't dive into it, but here I'm just gonna explain it more a little bit about the inspection score. So, inspection score is like a measure of the quality of the property in general, because it basically is like the property, the public housing we just mentioned, is given an overall score. The score is going to be between 0 and 100, and this numeric value of score is the cumulative total of separate like numerical scores, and obviously it depends on many factors like the community itself, some building exteriors, like in general, what the building looks. I mean, what the building look like, and do it look good or bad, and the building systems, like the more functional part in the building, like whatever the water, the heat, the gas, electricity, but basic utilities, and um, so on and so forth. It's basically like the internal systems. So common areas, like the places where neighborhoods can share, it means to have the units for each individual unit in the building. And I also want to mention another concept that we didn't really dive into last semester, and but we kind of touched on this concept of FEMA region. FEMA region is basically we are dividing the United States into 10 different regions, and based on their geological location. And I briefly mentioned this over the in-person meeting, a couple of days ago, but this is going to be a more detailed one. And basically, you can see in this map, there are like 10 regions based on the um, you know these some states are close to each other, so basically they're in the same region. As we can see, for let's say Ohio is obviously in the Midwest, and we have other regions like New York is in number 2, California is number 9, Florida is number 4, Texas is number 6, so on and so forth. So we're kind of breaking the United States into 10 different regions. This is what we call this something called FEMA region. That's a really fancy word, but it's basically like 10 different regions in the United States. Last semester we did like the research questions, and basically the thing we're interested is public housing inspection score. The first factor that can potentially affect the inspection score we propose is the flooding factor. I'm gonna dive into more like variables, like quantitative variables later. But the idea is flooding can affect public housing inspection score. The other dimension or the other factor or contributing factor is the demographic information um, that can also affect public housing inspection score. Um, the demographic information is going to be like ages, sex, gender, income, jobs, like so on and so forth. And I've also onto I I also want to dive into the message part. Uh, I mentioned briefly on Wednesday that the same the work I did last semester was divided into three parts. So we can this video I'm going to show you the detail of the three different parts. So we have panel data analysis. First, we start with I started with exploratory data analysis. It's going to be descriptive statistics, very basic data visualization without any like advanced analysis or um, transforming techniques. Second one is going to be second part is correlation analysis I call, and it's more like visualization um, than correlation I would say. So in this part I dive into the flooding factor that can potentially affect public housing inspection score. And the last part, I briefly mentioned that also on Wednesday, is the regression analysis, where I fit a linear regression that both accounts for demographic factors and the flooding factors. So the result right now in last semester was preliminary, is limited, but we already have like an overview of a general idea of the regression, like the relationship between these variables. So for exploratory data analysis, I spent like a month-ish last semester doing this kind of work, and the information that I found could be potentially valuable is going to be the following. So first of all, we have descriptive statistics. So we have inspection score, right? So why not we get the statistics of um, inspection scores both across different states, but also across different years over time, right? So here, I mean, in final presentation, I definitely didn't switch to GitHub and talk about this, but just for the purpose of this video, the work I did last semester, as I said, I spent almost 1 month doing the exploratory data analysis, and then in this repository, there are three branches, and I'm responsible for one of the branch. It's called Yusen. So if you click on this branch and inside of the figures directory, this is where I have all the results, and in the scripts, since the names of the scripts are self-explanatory, and each one is going to be like this one is a bit longer, but it's not going to be like in general it's like within 100 number of lines. And without diving into the code, let's look at the figures first. So inside of the figures, we have different folders, obviously, and these three CSV files, these are the descriptive statistics I got from last semester. So back to our presentation, we want to know the descriptive statistics across different states, but also across different years. So if you go back to the repository, we have three different CSV files. Let's look at the years one. So this result is the overall public housing inspection score over years. So as we can see, count is basically number of observations, and we have mean, standard deviation, minimum value, max, and we have three different quantiles. And basically, it measures data from 2008 to to 2020. Um, this is the data of inspection score in US as a whole over years. And the other thing in this analysis part is, of course, the descriptive statistics across different states. And by across different states, I mean both individual states like Ohio, Michigan, Minnesota, Pennsylvania, and the whatever, so on and so forth. But the other thing I want to point out is the FEMA region I pointed earlier. Um, we already got the data for FEMA region, but let's look at them like one by one, right? So the first one is a state. So for every single state, we already got the descriptive statistics for the inspection score. Let's say for California, the inspection score, the mean value is it's like 82, and for some other states, I don't know, Madison is 73, Michigan is 80, for Ohio is 80, for Texas is 84, and so on and so forth. So basically, this is inspection score, not over time, but across different states. So every single state, we know like the general or the I don't know the basic the basic distribution of the score, and what's the mean value, what's the standard deviation, like how varies are these data points. And the other thing is the FEMA region I mentioned earlier. So if we open this file, we have 10 different FEMA regions, and we already have the data for mean, standard deviation, and just quantiles over time, not over time, across different regions. So we have 10 different regions, and if we go back to the FEMA region, you can easily see like Ohio is in 5, and some other states are in a different region. But the idea is we already got the descriptive statistics from last semester. And the second part of explanatory data analysis is data visualization. And this part is not going to, it wasn't super complex. It was the most basic data visualization that we could do. Basically, according to the kind of information we wanted, the first thing we did is to build some histogram, and these histogram are like if we go back to the figures, and if we open the in regression distribution over year, and here we have two folders. One is called histogram. Did I spell histogram correctly? I don't think so, but anyway, the other is called line plot. So we can go to the histogram first, because this is the first thing we had in our exploratory data analysis part. So histogram, right? We open this file. Basically, let's do like 2020. These histogram are displaying the following information: is the inspection score in each year. It's basically like the distribution of the inspection score over a year, over 1 year, within 1 year, right? So if we look at this plot, it's going to be you see most of the observations are like probably like 70, 80-ish. So within 2020, we see this distribution of the inspection score. If you choose like different year, like 2019, it's a different distribution. 2016, it's different distribution. 14, if we go back to 2008, So this is like it's a very basic visualization, but the idea is within each year we know how the expression score data is distributed. It's very important because first of all, before like analyzing data, we can have to do some basic visualization for it. And this is by year, right? Every year we have different expression score histogram, a very different distribution um, over the United States. And the other part is the line plot. Basically, is there is another folder under figures. It's called line plots. There are a lot of pictures over there, but let's just figure out. Let's pick the US one. So these line plots are focusing on the other dimension of panel data. Remember, we have panel data. We could analyze panel data over different places. It's like what we did in the histogram. Like we see in 2020, the basic distribution of the expression score. But here we're focusing on the time or the timing factor of the panel data, and basically we are keeping track of the expression score over years or over time to see how how the expression score has been changed. So this is for this plot is specifically is from 2008 to 2020. It's the overall expression score in United States. So it's like the cumulative results for the entire United States of America. Basically, we see in 2000, we have some like turning points over here. The expression score is dropping over time, and this is captured by both median and mean. Um, I wasn't sure which one is better, but I think the both of them they share the same trend. Like it increased a little bit in 2015 and 2016, and then it's like decreasing over time right now to 2020. The both mean and median are not as high as before. And we also have the plots for other states, right? We have like say Ohio. This is a expression score over time in Ohio. Like in different years, we have different expression scores. But more importantly, I want to point out is that we already have the data for FEMA region too. So for every single FEMA region, we already know the inspection score over time. And for different region, it could be very different. Like say FEMA region 5 is just like it's like some I don't know some mass function is like fluctuating, but for some other region like 8, 9, like they have really different patterns, and this is also very interesting that for different FEMA region, the inspection score, the trend in inspection score can be really different. But this is like as I said, like basic visualization. We didn't dive into why this is happening, why this kind of things occur, but you got the idea of have FEMA regions, we have each individual state, and we also have we have the United States in general. So, as I said, this is a part for exploratory data analysis. And the second part is called correlation analysis. It's more advanced visualization and kind of dive into can some independent variables be correlated with the dependent variable, which in our case is basically the inspection score, right? So as I said in the meeting on Wednesday last semester, I focused on two important quantitative variables. One is called distance to flood zone. It's like the distance to flood zone, like how far are you from a flood zone, right? And the other variable is called is flood plain. It's like is this specific region inside of a floodplain? Like so for some regions, you're in the floodplain, and floodplain it doesn't cover like obviously it doesn't cover the entire United States, but it exists in the United States, right? The floodplain can be anywhere, and the variable is like, is this specific region in a floodplain? So these two are kind of correlated, but the idea is um, the correlation analysis. And if we go to the GitHub repository, there is a folder under figures. It's called correlation. Um, of course, as I said, there are two variables. The very first variable is distance, which is the distance of the region from the flood zone, the closest flood zone. So if we open this folder, I implemented this correlation analysis um, using scatter plot. So before diving into some FEMA region analysis, let's see the flood zone information for entire United States. So here is the scatter plot. So what is this scatter plot about? It's basically in horizontal axis is the distance to flood zone, and as we are increasing the distance flood zone, the expression score also it's also changing, and the y-axis is the variable we're interested in, the dependent variable or the expression score, right? Because all the work I did last semester was about expression score. So this is the scatter plot, and interestingly, this plot I didn't take all the data. I didn't take all the data because some points they can be very, there can be like many outliers there, and it doesn't really say anything about this specific trend or any patterns in it. So in terms of implementation, I truncated the data. I took the middle 50% of the data, and I got the scatter plot, and also fit a linear regression line over there. Um, the correlation or the coefficient is not as significant as you can see, but it's also because since we didn't like normalize the y-axis and the x-axis, but we can see like a slight positive correlation, which also makes sense. It's like the farther you are from flood zone, the less likely you're gonna get like affected by flood zone, right? So in theory, you can get a higher expression score, and this is also what this figure says. And this is for the United States, right? And then we also have the data for each individual FEMA region. Let's say for FEMA region 1, interestingly enough, I'm not saying it's interesting enough. It feels like a negative correlation there, and it's really interesting because it's really counterintuitive. Like the closest you are to a flood zone, you actually have higher expression score. But keep in mind, like the distance to flood zone is not the single like factor that can affect the public housing expression score. So yeah, there are other factors that are also playing a role. Let's pick a different region, like FEMA region 5. FEMA region 5 is also decreasing. FEMA region 7 is more like increasing. FEMA region 8, well, it's more scattered, but it's still like a positive correlation there. So I'm not gonna go through each individual plots, but the idea is we use scatter plots to capture the correlation between the distance to flood zone and the inspection score. So if you go back to the presentation, there is a second variable is floodplain, which is the final variable is this region in floodplain or not. So in this case, we have a different folder. It's called floodplain, where let's see, I implemented using box plot. So we have two columns or two colors. One is those specific places, areas that are in floodplain. As we can see, this plot is the blue box, right? And other regions that are not in floodplain, so they're in the yellow. They're in the yellow region, right? So as we can see, mm, if your region is in floodplain, the box says the inspection score as at least the media, if the media is going to be a little bit slow, it's going to be a little bit lower, right? This is what we can see from the plot, and it can also vary more if you're a floodplain. The inspection score can be also like very subject to change, which are pretty interesting. And we also have the data, the box plot for each individual FEMA region. Is that for each of them? I think for some plot they in some like the column is like missing. Let's say for FEMA region 8. The reason is that not a single place is in floodplain. So this part is kind of not that useful. But I'm just going through the process of like, hey, we're not only interested in the United States as a whole, but we also care about each individual FEMA regions. We can pick like a random FEMA region, like FEMA region 1. In this case, we also find out something that is counterintuitive. That you're in floodplain, but you still have a higher inspection score. I mean, that can be accounted by other factors for sure. But as you can see, for different FEMA regions, we have different patterns, we have different trends. With respect to the inspection score. So this is a correlation analysis at the last semester. And the very last part of the analysis I did was the regression analysis. Regression analysis is linear regression. Is a statistic model. It's not the best model for sure. We have, you see, I'm the CSE guy. I knew a lot of machine learning models. Linear regression is definitely not the best one, but it's the easiest one for sure. And it's not that bad. It's like linear regression sometimes. It's not that bad. So we definitely have to do more work in terms of regression analysis. But I'm just gonna show you these things. I'm gonna show you any work I did last semester. So for regression analysis, of course, we have, as I said before, we have flood factor, and the other factor is demographic information. So for the flood zone information, this time I only fitted this with this set of flood zone. I didn't fit linear regression with is in floodplain. Because I don't think that's gonna be super useful because both the binary variable is in floodplain and the continuous variable the sensor flood zone can be like really similar. We can definitely add it later for more comprehensive, more rigorous analysis for the regression, right? So flood zone information, and then we have demographic information. So these four variables are advised by Dr. Bass last semester. She was like, hey, Yusen, can you first of all look into these four demographic information to see if there is any regression property with the inspection score. So these four demographic categories can be age, how old people are, and the second one is more like the race or an ethnicity consideration. It's like white percent, what percent of people in the region are white, and third one is income. Lower income, middle income, like upper income, like these income can also affect the inspection score. And the last one is the renter percent, like how many people are here are actually the renter of these public housings. So, with that being said, let's go to the repository. Under figures, there is a folder called linear regression, which is very surprisingly it's linear regression, right? So under this linear regression folder, we one interesting thing I did last semester was first off I used the sklearn, which is the standardized machine learning model because I'm CS major. I'm like more into sklearn. But then I figure out like the sklearn it only derives the equation itself, but it doesn't give you any statistic significance about each individual thing, like about each individual like features, each individual independent variables. It gives nothing but the equation itself. So it's not gonna be that super helpful. So last semester I used another Python package, which is also commonly used. It's called stats models, and in that specific package, we can basically get such um such rich and comprehensive results that it does not only tell you the coefficient, but it also tells you the standard error, the t value, the p value. Um, it gives a lot of things that I think I personally understand, like maybe like most like 40% of this graph. But the idea is, if you look into this summary table, um, we can pretty much read the constant over there. This is going to be the coefficient. As we can see, the distance to flood zone is a slight positive correlation. For age, is negative. It's more like the younger you are, right, the higher the expression score is. Y% is also like a positive correlation. The more white people are living in a region, expression score is actually be higher. And then we have income. Income is really interesting here because you see, like the more money people they get, it doesn't really increase the expression score, but otherwise, but it's like the opposite is true. Like it's it kind of I don't know. This part is really interesting. I also pointed out this. I also pointed this out in the final presentation last semester, and I will show you later. I will show you this in a while too, in a little while too. Like a renter percent positive correlation there, and for these numbers, they're not just numbers, right? Because we have to know the p values. See, are these coefficients that are actually um, statistically significant? And one thing about age is that it's greater than the most common p-value, which is 0.00, which 0.05 is greater than it, so it's not that significant. But I still honestly include it in the results section. So in results, I already discussed this before. We have descriptive statistics. The range from 2008 to 2020 is going to be the approximate range is like 75 to 85. It's not going to be super low like 60. It's not going to be super high like a 95. And then we have the descriptive statistics for 10 different female regions. The range is still like 75 to 85, not really low, not really high. So data visualization, as I was already pointed out in GitHub, line plot over years, scatter plot, box plot, and the linear regression result table I just introduced. Yeah, and some demographic information. Um, already explained this, already said this before. Conclusion, the future work. Uh, we don't have substantial conclusion over here. We just have some like basic ideas. First of all, flooding factor can affect public housing inspection score. Second, demographic information can also play a role in influencing the public housing inspection score. Future work we gotta do more. I think I already have the female region, at least some preliminary analysis for it. But I didn't include it in the final presentation because of time limits. as well as I didn't really the work I did was not that perfect, was not like that detailed in terms of memorization process. But future work, we can add more stuff to the regression. Um, Also, last semester, I do want to point out, this is a reference in the session. We don't have to worry about that. Last semester, I also did fixed effect model. I was super confused. I have no idea what that is. Like, what the heck is the fixed effect in regression? So I still have something. It's called under FE regression. I don't know if you take any classes or if you know fixed effect in the regression, because that thing does not make sense to me. I think I spent a couple hours searching online, looking it up, ChatGPT, whatever. It's not making sense to me yet, but I will try my best to do it again. Definitely. Um, but here's the deal. We have this like really table and part of it is like I'm not able to understand this number. So this definitely gonna be something we have to tackle with this semester because we already included the fixed effect model, abstract. So we're expected to, excuse me, we expected to get the result. We expected to actually do something about it instead of just being like, oh, I got these tables and then I don't say nothing about it. But yeah, this is like the some upcoming tasks we can do. But I think that's pretty much it for it's like a really detailed video. Apologize, it's really long. It's very detailed. I covered almost every single aspect I did last semester, and I'm definitely looking forward to see you next Wednesday. So we can talk about any questions you have or any advice you could give to me, and we can discuss anything. I can help you, and you can help me. Yeah, but like this is just like the video is very comprehensive. It's really long. I apologize. Don't watch it like in middle of the night. So, but like yeah, that's the video for the a summary. Yeah, it is summary, right? It's a comprehensive summary of the work I did last semester. So, let me know if you have any questions. So we're gonna discuss on that on Wednesday. Yeah, thanks.